Let's go our final day of selections, and let's start right off the bat by revisiting truth tables. We covered in the last video several logical operators, and, or, and not, and we looked at those truth tables, and it's worth starting here in this video with a reminder of those. So A and B. So what are A and B? In another course, you learned that A and B are called propositions, which are statements that are either going to be true or false in and of themselves. So here we have this value A, which is a Boolean value containing either true or false, and we have this value B, a Boolean value containing true or false. If I tell you, and I did not show you this table here, if I said, give me all possible combinations of A and B, you could say, well, A and B could both be true. A and B could both be false. And the other two possibilities are A could be true and B could be false, and then finally A could be false and B could be true. So if you make all four of those possibilities, which you see here, and then we want to say, well, what is the truth value of A and B together, right? If I were to say, using an example last time, that right now I am on slide 79 and I'm talking about chapter 4 selections. I said two things. I'm on slide 79 and I'm talking about chapter 4 selections. That is not a complete true statement, because since I said and in English, and one of the statements I made was a false statement, therefore we can say the entire statement was false. In fact, the only time that A and B is true is when you see here when both A and B are true. If I say, I am reading page 75, and we are talking about chapter 4 selections. Those are both true statements. Because I use the word and, then we can see that because they're both true, the entire statement is going to be true. But if either one of the statements were false, or if they were both false, then the complete compound Boolean expression, or that complete statement, would be false. Or, when is that one going to be true and when is it going to be false? Just don't overcomplicate this as it says. Think about it in English. If I were to say, I am reading chapter 4, or we are covering chapter 4 selection statements, or I'm on page 50. Well, that's a weird statement to make to begin with, but nevertheless, because I said or I'm on page 50, then only one of those two statements has to be true in order for the entire statement to be true. So in fact, the easier way of thinking about or is to say that A or B is only going to be false when both A and B are false. So if you see here, here's the or column. It's only false when A and B are both false, but otherwise or is always true, meaning as long as one of the values A or B is true, then or will be true when you or them together. Of course, if both of them are true, then the entire statement is true. And then not A was pretty simple. It's just negating the value of A. So if A is false, not A is going to be true. If A is true, not A is going to be false. The same thing for B. If B is false, not B is true. And if B is true, not B would be false. This very important reminder. However, there's still some common mistakes that new programmers make when we're trying to translate an English statement into a Python Boolean expression, in particular a compound Boolean expression, which is using these logical connectors, these logical operators, to connect multiple Boolean expressions together. So what we have here is an example, and it's an English statement, x is equal to 5, or x is equal to 7. A common mistake is to say this right here, x equal 5 or 7. So let's break down that and see why it is in fact a mistake. If we say x equal 5 or 7, and this is a Python statement. It's an incorrect Python statement. Let me make this clear, it's an equals. What happens is the following. This gets evaluated, which is going to be either true or false depending on the value of x. So if x was 5, that would be true, right? And we're left with true or 7. Well, what is true or 7? You can't This is right here is a logical operator. On the left of that logical operator, over here, we must have a Boolean value, and over here we must have a Boolean value. You can't or true with an integer. That doesn't make any sense, right? So that's a problem because this is not a Boolean value, so that won't work. It's a common mistake. And of course, even if x was not 5, had x been something other than 5, let's say x had been 8, well then this would be false. And you're left with false or 7, which again makes no sense because when you're doing an or, on the left we need a Boolean value and on the right we need a Boolean value. And so you clearly cannot or a Boolean value with an integer. That's a problem. So how do we solve that? What is the correct way of writing this? Is you have to write two full Boolean expressions that each one individually will evaluate to true or false. And then you can use this logical operator or to connect those two results. So the correct answer would be x equal 5 or x equal 7. So if x is 5, this will evaluate to true. And it doesn't really matter what is on the right side because true or anything is true. Or let's say that x was 7. This would be false and this would be true. False or true would be true. And finally, if x was neither 5 or 7, we would have here false or false, which is false. But a common mistake is to write that statement like this. And we have a Boolean expression on the left and an integer on the right, and you cannot connect those two things with a logical operator. So with that reminder in place, let's now solve a relatively easy problem. I'm going to skip these check yourself, or we'll cover this first, then we'll solve the easy problem. This was just a reminder from last time. In the last video in the series, we covered this as well, but we'll look at it again. Good reminder to start us out. True and 3 greater than 4. Well, true and, now we have 3 greater than 4. That's going to be false. True and false is absolutely going to be false. What about this next one? We have x greater than 0. We said assume x is 1, so x greater than 0 is true, but not true is false. And then we have false anded. We don't care what comes next. An important reminder that if you have false anded with anything, let's erase this. If you have false and we can have over here a million trues. False anded with true to infinity, the entire thing will be false. Very important to remember that. And in fact, because computers are intelligent, or not computers, because programming languages and their respective compilers or interpreters are intelligent, they don't even waste time evaluating this right side. As soon as they saw that the left side is false, it's called a short circuit operation, and on the right side, it will automatically be ignored, and the entire thing is, of course, false. Here we have x is greater than 0, which is a true statement, or, and once again, this is another short circuit operation, because once again, we now have true, or I can make here a million falses, or together. False, or, and we can just keep on going to infinity. True ORed with anything will always be true. So once again, the way the interpreter in Python works is it doesn't even waste time evaluating this right side of the statement, and that's true. Here we have the next one. I already showed the answer. 1 greater equal to 0. 1 does not equal to 0 is a true statement. True or anything is true. The next one as well. X is greater or equal to 0. 1 greater or equal to 0. That's also true, so we ignore the right side as well. And then we have this last one. 1 does not equal 1. That is a false statement. So on the left we have false. Now let's look to the right side. We have not x equal 1. Well, let's look at this parentheses first, right? We do what's inside the parentheses. 1 equals 1 is true. Not true is false. So we're left with false equal equal false, and that's actually a true statement. There's no and or there, just does false equal false, and in fact it does, which is kind of funky at first when you see it, but just think about it. Does false equal false? Does 7 equal 7? Yeah, false in fact does equal false, so this will be a true statement. So now let's solve this easy problem. Write a program to check whether a number is divisible by 2 and 3, by 2 or 3, or by 2 or 3, but not both of them. So let's start by examining the output. We're going to ask the user to enter an integer, and we're going to then simply print the result, that given integer 18 is divisible by 2 and 3. Independently, we're going to check if it's divisible by 2 or 3, which of course, if it's divisible by 2 and 3, it's going to be clearly divisible by either 2 or 3. And then also independently, we're going to print whether it's divisible by 2 or 3, but not both. These are just going to be 3 independent if statements. So let's go over to Thani. Let's start this out. We need to do what? Ask the user to enter an integer. So let's start by doing this. Let me hit save. And what do we want to call this? Test Boolean operators. Why not? This is chapter 4. Test Boolean operators. And we need to ask the user enter an integer. Prompt the user to enter an integer. Let's call it number. Let's call it num equals input enter an integer. Easy enough. And now we need to test if it's divisible by 2 and 3. So check if num is divisible by 2 and 3. So if num, and how do we check if something is divisible by 2? That means we can divide it by 2 and it has no remainder. How do we check if it's divisible by any number? If we check if it's divisible by 3, divide it by 3. If there's no remainder, it's divisible. So we want to divide it by that number and then check its remainder, which as we know by now very well, I hope, that's mod. So I can just say if num mod 2 is 0, if we divide it by 2 using integer division and the result in the remainder is 0, it's divisible by 2. And num mod 3 equals 0. If that's true, print the following. Let's print this using formatted printing. Blank is divisible by 2 and 3. And then we say dot format, and this is going to be num. Easy. And let's copy paste, save time. Copy all of this. Now we want to check if num is divisible by 2 or 3. Now it really makes sense. I'm gonna put this first. It doesn't make sense to put that afterwards. I'm gonna do it this way. If it's divisible by 2 or 3, if it's divisible by 2 and 3 will come next. But let's work on the or 3. If num mod 2 equals 0 or num mod 3 equals 0, we'll say that num is divisible by 2 or 3. That's all we did. Look how easy it was to make that change. And before we do the final check, that final statement where we're checking if it's divisible by 2 or 3, but not both of them, let's go ahead and run this with 18, was it? 18 is divisible by 2 or 3, because in fact 18 is divisible by 2 and 3. It is divisible by both of them. So what was the final one, which is the harder one to do, but I want to put it here. It makes logical sense to me to put it here before we check if it's divisible by both. And so this one is check if num is divisible by 2 or 3, but not both 2 and 3. So this is going to be a compound statement here. We're going to be checking first this statement that we already have. I'll just copy this entire thing. So what do we want to print? We want to print blank is divisible by 2 or 3, comma, but not both. I'll write it even more detailed, but not both 2 and 3. So the real question is, what do we do here? How do we take care of this? Num mod 2, we want to check if num is divisible by 2 or 3. We've already done that. That's this. But not both 2 and 3. So what we want to say is we want to say, and it's not divisible by both of them. So now how do we convert that to code? And so we're checking 2 different things. Check to make sure this part's true. And if you feel better about it, you can put this in parentheses. You don't need to. But check to make sure it's divisible by 2 or 3. And when you're done, check to make sure that it's not divisible by both of them. Well, guess what? This right here is checking that it's divisible by both of them. We already have that. So let me copy that. I'm going to put a pair of parentheses. What is this now doing? Compare this. This is not the answer, but translate this to English. This is saying if it's divisible by 2 or 3, and if it's divisible by 2 and 3. Well, that's not what we want. We want if it's divisible by 2 or 3 and not divisible by 2 and 3. So that takes a moment to do that and think about it and wrap your mind around it the first time, maybe even the second time, because that's a sizable compound Boolean expression, right? We have these already compound Boolean expressions on the left and right. Then we're using another logical operator to connect them, and we're even negating this entire one because we're saying that it's not divisible by both 2 and 3, because this is divisible by both 2 and 3, and here we're saying not divisible by both 2 and 3. And this is how you could have solved the problem. Now, if you had paused the video, which would be great if you did, and if you had tried to code this up yourself, you may have come up with a slightly different way of thinking about it, and it would be correct. The way you may have thought about it is you may have said, let's see, and not num, this would be or, let me get rid of the not, and this would be right here, does not equal 0, and this would be does not equal 0. This would be another way of thinking about it. What does this say in English? This says that num is not divisible by 2, right? Because it's not equal 0, so it's not divisible by 2, or num mod 3, or num is not divisible by 3. Sorry, let me say that again. This says num is not divisible by 2, or num is not divisible by 3. That's logically the same as saying that num is not divisible by both of them. It's the logical equivalent, and in fact, that's a law that I'll show you in just a moment. So there's 2 ways we could have solved it, and I did something wrong here, is I kind of skipped the analysis first of problem-solving phase, which I'm saying we have to start. That is where's my big brain? That is a big brain moment. Let's skip the problem-solving phase, even though I did talk about it briefly. But we need to simply, of course, read that value and then have the if statement. So it's straightforward, which is why I jumped right to the solution. But in the solution, we still cover that problem-solving phase. And here is an implementation where I showed both of those possible answers at the bottom. So where's that second answer even come from? It's called De Morgan's law. It's a famous law used with Boolean expressions. And it's simply saying that if you have not, and then you have a compound Boolean expression that is connected with the logical operator and inside, that's the same as doing what? You effectively can distribute this not to both of the conditions, and then you have to flip the and to an or. Does that make sense? You have to flip the and to an or. So hypothetically, if I had not A and B, that would be the same as not A or not B. Also, if I had not A or B, that's the same as not A and not B. So the not gets distributed, and then the A flips over to an or the or changes over to an A. It's called De Morgan's law. It's a famous law with Boolean expressions. So we had this line, and if you effectively distribute that not to this Boolean expression as well as to this Boolean expression. And I see here that I'm missing an and in the middle. It's a typo. I forgot to type that and. So we'll have not number mod 2 equal 0, which means it's not divisible by 0. So we can just change the equal to not equal. Or number mod 3 does not equal to 0. So logical operators. Let's write several of these to test these ourselves. Write a Boolean expression that evaluates a true if variable num is between 1 and 100. Pause the video. Try to knock that out. Write a Boolean expression that evaluates the true if the variable num is between 1 and 100. Pause and then knock it out and come right back. The answer is this: num greater than 1 and num less than 100. So you need to have two independent Boolean expressions that both will ultimately evaluate to either true or false. And then we simply connect the results of those two expressions with this logical operator and. Another one, write a Boolean expression that evaluates the true if the variable num is between 1 and 100 or if the number is negative. Once again, pause the video. Think about that. Just write it down. Just takes 15 seconds. The first part is the same if it's between 1 and 100 or the number is negative. Here's an answer. You take the entire first part that we already did and we solved correctly, and we simply say or num less than 100. Not that hard, but we probably overcomplicate that. We're like, oh, it sounds so complicated. It's not that complicated, and I can turn off my big brain. It's a big brain to leave the big brain on the screen the entire time. I just noticed it was still there. It's fantastic. All right. Another one, write a Boolean expression that evaluates to true if weight is greater than 50 or if the height is greater than 160. You can pause the video, but I think you can do this one quickly at this point. Answer, weight greater than 50 or height greater than 160. Pretty straightforward. I think we're getting more comfortable with the fact that we want two independent Boolean expressions. Write a Boolean expression that evaluates the true if either weight is greater than 50 or if the height is greater than 160, but not both of them. And this is what we just covered in that larger example that we coded together. Write if one of them is true, the weight is greater than 50 or the height is greater than 160, which is what we already covered above, but not both. So then we're going to say and not weight greater than 50 and height greater than 160. So we're at another problem. Determine if a given year is a leap year. This is not a hard problem. Most textbooks will be using this problem when covering or during their coverage of Boolean expressions. Why? Because the mathematical rule for determining a leap year is a complicated, convoluted Boolean expression. This is really a simple program. You're really going to just ask the user, enter your year or enter a year, and then you're going to print if it's a leap year, yes or no, based off of the truth of this, what seems initially to be a convoluted Boolean expression. And we'll go through it. So problem-solving phase, leap year comes every 4 years, as we know. But how do you know if a year is a leap year? It's a mathematical-based rule. And here it is. A year is a leap year if it's divisible by 4, and that's what most people know, if it's divisible by 4. But the other part of the rule is two things. It can't be divisible by 100. So a given year is a leap year if it's divisible by 4, but not 100, or if it's divisible by 400. So think of some years. The year 2100. That is divisible by 4. But it's also divisible by 100, so it's not a leap year. The year 2200 is divisible by 4, but it's divisible by 100, so it's not a leap year. Same thing goes for the year 2300. It's divisible by 4, but it is also divisible by 100, so it's not a leap year. But now let's check the year 2400. The year 2400 is divisible by 4, but it is also divisible by 100, so you might say, aha, it's not a leap year, but there's one final component. If it's divisible by 400, it's absolutely a leap year. which the year 2400 is a leap year, even the year 2000, which is divisible by 4 and 100. So you might think, oh, it's not a leap year, but the year 2000, of course, is divisible by 4 because we see that you can get a clean 500 is the answer. 500 times 4 is 2000. So it's divisible by 400. Therefore, the year 2000 is a leap year. Funky rule if you didn't know it, but that is the rule for determining if a given year is a leap year. So here, if we build this out in steps, we have this variable is leap year, and let's build it out in steps because let's be honest, this rule is a long rule. So don't try to do it all in one go. Do it incrementally. Is leap year equals year mod 4 equal 0. It has to be divisible by 4, but what's the second step? But not divisible by 100. So add that in there. So year mod 4 equal 0, and we could have said and not year mod 100 equal 0. I could have done that. Right? Let me come code this over here. Garbage. I could have said is leap year. Let's come above and say year equals 2000. I could have said is leap year equals year mod 4 equal 0, which is what we have, and not year, and I'll connect these with parentheses because some people like to see that, and not year mod 4, year mod 100 equal 0. That's what the rule says, that it's divisible by 4 but not 100. That's what this is. But of course, not divisible by 100 is the same as simply saying this, right? I got rid of the not, and here I'm saying it's not divisible by 100 by virtue of changing the equals to exclamation equals. That's the same thing. So it's divisible by 4, but not divisible by 100, or it is divisible by 400. That's the last condition, which goes independent. So this is going to be, all of this goes together. So whether or not we use these parentheses around each of these individual things, that's not necessary. But regardless of whether you do use those individual parentheses or you do not, we absolutely need to put all of that in parentheses because all of that goes together as one statement. And then we say, or the year mod 400 equal 0. That trumps it all. If the year mod 400 is 0, it is absolutely a leap year, period. And we can print year is a leap year. Simple dot format year. That was fantastic. I did not actually do a Boolean expression there. So let's do this. If is leap, wow, I cannot type, is leap year. If this is true, so this is just, this right here is an assignment. We're doing a Boolean expression. We're determining if it's true or false, and we're assigning it into this variable. So if it is true, we're going to print it's a leap year, else we're going to print that it is not a leap year. Paste is not a leap year. So if you check 2000, it is a leap year. You check 2100, it's not a leap year. 2200, not a leap year. 2300, not a leap year. 2400 is a leap year. So where are we at right now? We're at the year 2023. When's the next leap year? It should be right here. This is divisible by 4, but not by 100. So that, in fact, will be a leap year next year. So not the most exciting program, but it's a common one used in textbooks because why of this rule and converting this rule to this long, seemingly complicated Boolean expression. All right, we're almost done here. Something interesting, maybe it's cool that most languages will have something similar to this. In Python, we have conditional expressions, and it's unique where the idea is that we can have a single line that will evaluate this if-else condition for us. So consider these 4 lines of code. If x is greater than 0, y equals 1. Otherwise, y equals minus 1. So we have the situation where we're trying to assign a value into the variable y based off of what is inside x. If x is greater than 0, we assigned y the value of 1. Otherwise, we assign the value of y to be minus 1. Pretty straightforward. So what's funky here is that when we do this, we can see that Python can actually make this happen in one line of code. Y equals 1 if x is greater than 0, else minus 1. That's one line that does all of it. Y is 1. If x is greater than 0, else it's minus 1. It's funky. There's not much else to say there. If you like that, great. If you don't like it, great. That one line does what all four of those lines accomplish. So here's the overall syntax. You say expression 1 if the Boolean expression is true, else we put expression 2. We have another example. We have these two numbers, num1 and num2. We want to assign the larger of those numbers into the variable max. So we could write an if-else statement just like on the last slide. So we could have said if num1 is greater than num2, max is num1, else max is num2. We could have done that. Or you can just do this. Max equals number 1 if number 1 is greater than number 2, else number 2. Funky, but it works. And some students like that. Some students are like, that's pretty cool, you know, and they're happy. It seems shorter. We like short stuff. It makes things easier for us, right? Shortcuts, but sometimes it's not maybe the best with respect to clarity, with respect to software engineering. Readability purposes, the 4 lines are pretty easy to read and comprehend. Maybe this is less easy to read. So it really is a personal preference. So we've seen now a variety of new operators with these logical operators. It's time to revisit that precedence chart. So what do we know from basic elementary school in this precedence chart? We know, of course, multiplication, division. We know that exponents come before that, right? Of course, from PIMDAS, we have parentheses, then we have exponent, then we have what comes next is multiplication and division. Then we have addition and subtraction. So we already know those things. Well, interestingly, know that not is pretty high up on the precedence chart. Also, what is high up on the precedence chart are these comparisons. Next comes equality. Then we have and or, and notice they're not at the same level of precedence. And gets evaluated in Python before or. And if you don't pay attention to that, you'll get the wrong answer. And the lowest thing on the precedence chart are the assignment and the augmented operators, which are effectively assigning after performing maybe some mathematical operation, addition or subtraction or what have you. So with that in mind, check yourself on this. True or true and false. Now we just said that and gets evaluated first, so with that in mind, you probably remember that. But true or true and false, so if we start with the and, true and false is going to be false. And then we're left with true or, this whole thing was false, true or false is true. Now, had you, where's the answer? Is it showing somewhere else? No, okay, that's fine. So had you not known that rule and you started just from the left and you thought, oh, they're the same level of precedence, you would have said true or true, true, true and false, false, and you would have given the entire answer of false, and that would be incorrect. So and gets evaluated first, true and false is false, but true or false then becomes true. We have another one, true and true gets evaluated first, that's true. Then we have true or false, that's still true. This one, what happens here? Well, you got to break it down. Where do you see, and what do you see with respect to the precedence chart? We have multiplication, we have subtraction. We know multiplication comes first. We have another subtraction. What's left is we have greater thans and we have an and. So come back up, look at the precedence chart. Where do we see the greater than? We see that right here, and we see the and right here. So we're going to do the greater than first before we do the and, but even before that, notice we have the multiplication and a division and addition, subtraction. So we perform those mathematical operators first, then we do the comparison with a greater than, and then we do the and. So when we look at this, perform the math first, if we can. So we have 2 times 2 is going to be 4. 4 minus 3 is 1. Over here, we're going to have 4 minus 2 is 2. So now we're left with 2 greater than 5. That's going to be false. Over here on the left, we had 4. 2 times 2 is 4. 4 minus 3 is 1. 1 greater than 2, that's false. We have false and false. I encourage you to try this one, see what you come up with, and then maybe even code it up to check yourself. Final program, the lottery program. Write a program to play a simple lottery game. The whole purpose here is Boolean expressions and using these logical operators. Your program should randomly generate a 2-digit number from 10 to 99 inclusive. You should prompt the user to enter a 2-digit number as well, and then we are going to determine winnings based off of the following. If the user's input matches in the exact order, the award will be $10,000. It's a pretty good chance of winning $10,000. If all of the digits in the user's input match, but it's in reversed order, meaning the user entered 23, but the randomly generated lotto number was 32, well then it's the same numbers, but they're reversed. They win $3,000. Finally, if they only have 1 digit matching, they still win $1,000, meaning if the user entered 18 and the number was 84, well, they have an 8 that's matching and it counts. Or if the user entered 18 and the answer was 41, well, they have 2 1s and therefore it counts and they get $1,000. Maybe kind of cheesy. The whole purpose is to practice Boolean expressions with these logical operators. So we need to check if the guess matches the random number. That should be easy, right? You can just generate the random number, take the guess, use 2 equal signs to check if they're the same, they win 10,000. But what about if now we need to check, okay, well, what if it's reverse order? We need to get the individual digits. This is something at this point we're experts at. We've taken this number, for example, 57, and we've broken it down many times. How do we extract just the 5? How do we extract just the 7? That's going to be using integer division and mod to get the value in the tens place, to get the value in the ones place. Pretty straightforward. We're going to do that with both the user's guess as well as with the randomly generated number, and then what's left will be simply comparing all of those different values to determine the winnings. So we get those digits from the guess, we get the digits from the random number, we have the checks. If the original numbers are identical in the same order, the same exact order, they get 10,000. Or we could have just compared random number to guess, you get 10,000. Elift. If the digits don't match, but the digits match, but they're in opposite order. So if digit 1 from the user's guess equals digit 2 from the random number, and digit 2 from the guess equals digit 1 from the random number, they win 3,000. And then finally, if only one of the digits matches, they win 1,000. So time to go code it up. And here is an expected output of the program. Enter your lottery pick, 2 digits. So they enter 45, and the lotto number was 12. We say, sorry, no match. Enter the lottery pick, 23. The lotto number was 34, and we print that you matched 1 digit, you win $1,000. Let's go code this up. So file, new, save, chapter 4. And let's call this Lotto program. So enter your lottery pick is what it says. So prompt the user to enter their lottery number. So let's call this user number. I'll call it Lotto user. Sure. Lotto user equals int input. Enter your lottery pick. enter your lottery pick, 2 digits. And we also need to generate a random 2-digit lotto number, lottery number, lotto num, fine, equals. We want to generate this, so it's going to be random, which you need to import, random.randint 10,99. That's pretty straightforward in Python. Import random. And let's go ahead and set a seed so we can get the exact same values together if you're coding this. Random.seed. And let's put the seed here to be some number, 123. That's super creative. So generate a random number, prompt the user to enter their lottery number, and then what follows is print the results. So if lotto num equal, what is a better variable? The user is entering choosing their lotto number. So lotto user, that's fine. I'll call it lotto user. So lotto num, if lotto num equal lotto user, we can just print you won $10,000. That's super easy. And let me go ahead, and what else was printed? The lottery number is this. We need to print the answer. So first we're going to print the lottery number is, we'll use formatted printing just to be consistent and develop good habits, .format, lotto num. Okay, so if the user guessed the correct number, they win $10,000. So let's run this. Enter the lottery pick. Let's put 54. The lotto number is 16. Of course, nothing got printed because they didn't match it, and we didn't put those conditions yet. But now that we have a seed, we know the lotto number is going to be 16, right? So I'm going to put 16 now. The lottery number is 16. You won 10,000. Whoa, shocker. Okay, that's the value of the seed that we can now test it because we know it's going to always be 16 every single time we play. So I can choose 52. Well, it's still going to be 16. Okay, so now we need to do what? We need to get the digits on both the lotto number as well as the user's lotto number. So here, what do we want to call this? So before we print the results, we need to get the individual digits of both the lotto number, lotto num, and the lotto user. So these are going to be long variable names, but it will be super clear. So lotto num digit 1 equals lotto, let's just call it lotto num tens place. Let's do it that way. So it's good practice to know what we're doing. Lotto num, how do we get the tens place? We divide it by 10. And then how do we get the ones place? We mod it by 10. Lotto num mod 10. I'm going to take those exact 2 lines of code, paste, and now this is lotto user. Tens place is the lotto user divide 10. Lotto user ones place is going to be lotto user mod 10. So now we have the individual digits extracted. We are ready to go. And so now I'm going to type in else if the digits are the same but in reverse order. So Elift. And now we just need to check. We need to check and compare, does the lotto num tens place equal the lotto user ones place? So if lotto num tens place equals lotto user ones place and does the Lotto num ones place equal Lotto user tens place? If that is true, print, what do we print here? Matched one digit. You matched one digit. No, you matched both digits in reverse order. You win $3,000. And we'll put 2 exclamation points. Easy enough. Let's check this one. So I'm going to run it. And let's, of course, if we put 16, we know they won the full thing. Let's do it reverse order. So let's put 61. The lottery number is 16. You matched both digits in reverse order. You win $3,000. What is the Elift? We can't just put else. If we put else, what's the problem? We want to be able to say you matched only one digit. You win $1,000. We'll put 1 exclamation point. Well, what's the problem if we put else there? Well, even if they don't match anything, if they put 75, clearly they didn't match a digit, so that's a fail. This will be the final else. The final else will be you did not match anything. Sorry, but you did not match any numbers. Better luck next time. Give an exclamation point. Okay, so that's the final else. So this is an Elift still here. Else if what? Else if only one of the digits matches. So Elift, we need to now check. This is going to be convoluted. We need to check if the tens place of the Lotto num matches this or this, the tens place or the ones place of the user. Those are 2 individual statements. We also need to check if the ones place of the Lotto matches the tens place or the ones place. It's all or together and it's really long. So Elift, check this out. And I'm going to put the print statement right now before I forget it since I copied it. So this is going to be nasty. Let me zoom out just a little bit. It's a long, convoluted Boolean expression. If this one equals this one, or I'm going to come to the next line, which you can do. And you'll see even here on the solution, I just came to the next line with each of the ors. So I'm going to put or. Well, let's see. I don't know. I'm going to type it all into one line. Then I'm going to test it if I can put it on the next line. Or, so Lotto number tens place equals Lotto user tens place. Or Lotto num tens place equal Lotto user ones place. Or Lotto user Lotto num, let me make sure I did this right, Lotto num tens place, Lotto num tens place. So I checked to see if it was Lotto user tens place, Lotto user ones place. Cool. So now I need to do the exact same thing. I'm just going to copy all of this without the or, right? I'm going to paste. But now what am I checking? I'm checking to make sure. So the first ones I was checking was, does the Lotto num of the tens equal either of the user ones? Now I want to check, does the Lotto number of the ones, right? So here's the first check. Here's the second check. This is the third one. So let's make this ones, and then let's make this ones. And that is the complete program. So when I run this now, let's type in 63. You matched one digit. We can type in 76. You matched one digit. We can type in 19. You matched one digit. We can type in 81. You matched one digit. All of that works. So out of just curiosity, where can, I did this on the slide, but can you? I actually have not tested this. Yeah, I would have thought that would have shouted at me. So let me see. I've never done that. This is actually from, let's see. I think that's just done here because Python is so strict with the spacing. I looked at that, I'm like, wait, that just seems funky to think that you can go put that like this. But there might be something that maybe about something new in Python being tabbed over. I don't think so. I don't think that's going to work because you have to be very clear, very purposeful with your indentation in Python. So that is a long Boolean expression comparing all of the different digits to each other, but hopefully it's clear. And that is our final program. Let's go. We're done. As always, reach out if you have any questions. Leave a comment. It's been fun. Take care, everyone.